Do you need a suspension for your racing vehicle which is double wishbone and uses a pull rod? Then look no further, we have exactly what you need. In this video we will be breaking down some of the design choices behind Group 19's suspension. Please enjoy.
This one-part rim made from aluminium 6061 went through multiple design iterations. Through the use of generative design, we were able to simulate different designs, such as changing how many planes of symmetry there was. Through manual design and FEM testing, the final rim has 4 large spokes, each with a large weight-saving hole, ensuring structural integrity, while also being as lightweight as possible.
The braking system uses the 4-piston AP racing caliper in order to achieve the required braking torque given the maximum disc diameter. The SBS soft organic pads are used, which provide sufficient braking torque with the 190mm disc diameter used. For the disc, a floating disc design is chosen, with the disc mounted to the hub using bobbins, spring washers and circlips, enabling improved thermal management by allowing for the disc to expand, minimizing warping of the disc. The disc is also drilled to improve surface area for cooling and is grooved to help expel brake dust.
The hub is part of the rotating assembly which links the rim, brake disc, CV joint and the upright and transfers torque between the drive shaft and the rim. While some dimensions were predetermined, such as the spacing of the rim bolts, brake disc and inner bearing shaft, the rest of the parameters were calculated using a spreadsheet that considered design and material factors. Trial and error was used to find suitable parameters such that the hub was strong enough. High yield strength and good machinability requirements meant that AISI 9255 low alloy steel was chosen after a material selection process in EduPack. Also, the CV adapter was attached to the hub with a central bolt.
The CVJ, or constant velocity joint, allows the rotating assembly to maintain the same velocity as the torque shaft, regardless of the suspension's vertical displacement. As the CV joint was provided, an adapter was designed to connect the component to the hub. The torque joint method chosen consisted of 6 axial dowel pins for both the hub and the CV joint, due to the simplicity of machining and its common use within industry. To ensure the pins could withstand the drive torque, several pin arrangements and dimensions were evaluated for an optimal solution.
The upright connects the static and rotating parts of the suspension system together, and therefore the pickup points are determined by the surrounding components and their calculations. Finite element analysis within Fusion 360 has been utilized to produce an adequate design and provide design validation while reducing mass as much as possible. Due to the different connecting components and the associated forces, the strength of the supporting material must be of adequate magnitude to avoid complete material failure, as seen here in the finite element analysis using steel. The upright has been designed with milling in mind, with a large flat rear surface for easier mounting during machining. Every corner, interior and exterior, has been curved to accommodate rounded bits used in milling. EduPack is used to find a new material that has a higher yield strength and similar density to default steel. Low alloy steel SAE 4335M, cast, quenched and tempered was chosen. The addition of the new material and some support strengthening brings the safety factor above the desired value of 3, which validates the final design, even though a localized high stress point is present, which can be seen here.
The upper and lower wishbones are here. They are designed to be welded together from 3 sections of tube and a plate to reinforce them. There is a swivel joint inside this tube which then acts as a ball joint. The pull rod is fixed to this plate with a welded bracket and extends down into the chassis here. The tie rod is attached here at the rear of the chassis using a section of tube which is welded to the chassis. We decided to mount it this way so that there would be an additional area to weld, increasing its strength. Also, doing it this way meant that a jig could be used to get the angle of the welds of the ears just right. A similar strategy is used for the rocker and the damper mount. We experimented with many configurations for the tie rod. It was in the way of the brake lines at one point, so we moved it to the opposite side of the upright, and we also needed to resolve some problems with bump steer, shown in this video. We found that making the tie rod a similar length and angle to the wishbones resolved our bump steer problems. The other chassis mounts for the wishbones and pull rod use brackets and a plate. The intention is that the plates would be welded to the chassis tubes, one in each corner, and then the ears of the brackets could be welded to the plates. Alright, I think that's all we've got time for. Thank you very much for your attention and time, and I hope you have a lovely day. Farewell.